Okay. Okay. Sorry, then I have to stop sharing over hand. Yeah, okay. Yeah.
Thank you, Ravi. Hello, everyone. Coming on to the speaker himself, Dr. Aninda Sinha is a celebrated theoretical physicist who works on string theory and quantum field theory. He was awarded the Shanti Swarup Bhatnagar Prize in 2019 for his influential work in the field, in particular on conformal, bootstrap, and entanglement entropy. He finished his BA and MA in applied physics at the University of Cambridge. He received his doctorate in 2005 also from University of Cambridge and wrote his thesis on aspects of IIB plane wave string theory. He has held postdoctoral positions at the Premier Institute for Theoretical Physics and at Cambridge. He is now a professor at the Center of High Energy Physics at the Indian Institute of Science. Dr. Sinha mainly works on string theory but has also conducted research on cosmology and black hole accretion disks. He focuses on mathematical and elementary particle physics, with an emphasis on quantum field theory, conformal field theory, and connections between quantum information and holography. Along with the Shanti Swarup Bhatnagar Prize, he is also a recipient of the Swarna Jayanti Fellowship, Ramanujan Fellowship, the ICTP Prize, and is a Simons Associate at ICTP. With that, I would give the stage to Sir. Over to you, sir.
Okay, thank you very much. Can you hear me? Hopefully, and you can see my screen, right? Can you see my screen? Okay, can you see my pointer? You can see this pointer here?
Yes, sir.
Okay. So, I'm going to talk to you about quantum field theory without Feynman diagrams. And now, I would really very much encourage that you ask questions during the talk, if you have any, because this will make it interactive. Because I can't see you, it's very difficult to react. And usually in person, you react off the reactions. So it'll help me out if you ask questions during my seminar. As theoretical physicists, if you maybe do a course in quantum mechanics, you know that we are interested in calculating probability amplitudes of various processes taking place. So here on the left, I have drawn a diagram. It's what's called a Feynman diagram. And specifically, it is what is called a tree-level Feynman diagram. So you have two particles coming in. Time flows in towards the right. So two particles coming in, interacting, and maybe exchanging some particle here, and then becoming two outgoing particles. So that is why it is called 2-to-2 scattering. This is how you say it. This is 2-to-2. If there were three particles coming in, you would say it is 3 to whatever. And if it is two particles going out, then you would say 3-to-2 scattering, and so on. And this is tree level because you will see that Feynman diagrams also have loops, circle type things, and those are difficult to calculate, and those are quite painful in many senses. We'll encounter some of them. So as maybe particle physicists, or even if you say you're thinking about something like quantum gravity, you would be interested in calculating the probability amplitude for such a process taking place. Now, yeah. Okay, so just 1 second. So let me stop presenting and present full screen. Let me just 1 second. So is it now visible, the pointer? And now? Okay. Okay. So if you think about it, to describe a process like this, suppose you are an experimentalist and you want to actually study such processes, you would require to make particles, particle A and particle B, and you require to measure particle C and particle D. Of course, you don't know what is happening here. That's why it's called a virtual exchange. But in order to actually calculate the probability amplitude, we would need to know about what particles can be exchanged. Otherwise, you won't be able to calculate anything. Now, this is all right if the spectrum of particles, sorry, what happened? Just 1 second, yeah. Let me just remove this. So if the spectrum of particles was simple, so what does simple mean? So by simple, I mean that there were some low energy particles here, so low mass particles. So for example, the graviton, electrons, these have low masses. And typically we talk about these particles which we know exist. So we know that electrons exist, we know that protons exist. So we know something about the low energy spectrum. But suppose the spectrum was more complicated. So you also have these high energy particles. So there is some gap here. And then there was some infinite number of high energy particles. And these particles were very massive. So you really cannot detect them directly because they're too massive, because you cannot excite them because you don't have enough energy to excite them in the laboratory. So if you have a situation like this, then how do you describe such a process? Because I said that you require to know what this virtual exchange is. And if you really don't know what this tower of particles is, then how do you calculate such a process? So if you're interested in talking about observables, things that we can measure, then we need a framework where we do not have to worry about what particle is getting exchanged. And does such a framework exist? Or also another thing that we would desire from this framework is that it should be versatile enough to count also for gravity. So that we can talk about a theory of quantum gravity. And the framework should constrain the theory space, because sometimes you have a framework that is so broad that you can sort of calculate anything that you want. I mean, if you, this is roughly in the spirit that if you keep adding more parameters in your, say, suppose you're trying to fit a data set, And if you keep adding parameters to your fit function, you'll always be able to fit that data set. But that is not how it should work. It should be that the framework is restrictive enough to constrain the theory space. So this framework that I'm going to describe to you is what is called the bootstrap, and is going to be the focus of my talk. So why is it called the bootstrap? So if you open the dictionary, bootstrap, naturally you start thinking about something to do with your boot, and that is what you might think. But that's not the context in which this is used. Now, the bootstrap is used as an adjective. It means that you rely on your own effort and resources, and you constrain things. So, for example, the business was a bootstrap operation for the first 10 years. So it was constraining enough, and it was able to generate enough resources. Or more specifically, it is a self-generating or self-sustaining process. So that's what it is called, a bootstrap process. So this is based on several papers that I've written over the last 6 years or so with on related topics. So it started with an exploratory exercise that I was doing with my very smart graduate student, Kalol Sen, in this paper that essentially was based on observations that he made. And then we understood the importance of what we were doing. I will describe some of that in detail. It involves my graduate students Apratim Kaviraj, Kalol Sen, and my collaborator and friend Rajesh Kopakumar from the ICTS. It involves postdocs, Parijat here, then my graduate students Kaushik Ghosh. This is my current graduate student Ahmadullah Zahed, and Pietro Ferrero is a student in Oxford. And then there are several follow-up works, which also includes why I have highlighted this in blue is because these are undergraduates. So these are this is Anjishnu Bose, who was a very smart undergraduate from IISc, Pratish Sinha, who was my master's student, and Shashwat Tiwari, also a very smart undergraduate from IISc, and which led to these publications here. I will also mention what the importance of these publications are. And this also involves work with my other graduate students, Parthiv, Ahmadullah, and my postdoc, Prashant Raman. So let's begin with something very basic. Let's describe quantum fields. So this picture should be familiar to all of you. This is Newton's law. You know that Newton's law is given by some inverse square law. This is Coulomb's law. Again, it's an inverse square law. So this is something that is familiar to everybody. But also you should be aware that there's a problem in this description. When we use this classical description and talk in terms of force, the problem is that this force appears to be instantaneous. Why? Because there is no time here. I mean, this equation does not involve time, and that is why it is instantaneous. And this is clearly in contradiction with Einstein's special relativity, which says that nothing can travel faster than the speed of light. So this force cannot be communicated faster than the speed of light. So there's something wrong in this description. It's, of course, a great approximation. That's why we still use it. But it is not compatible with special relativity. So what is the cure for this problem? So the cure for this problem at the quantum level is to use a description which is called quantum field theory. So historically, the first quantum field theory was written down by Dirac in 1927. So he wrote down a relativistic wave equation, which was the correct description of the electron. And his theory was quite predictive because it predicted the existence of antiparticles. It predicted that there should be electrons as well as positrons. So it basically took into account pair production. And you can say that this was the time where quantum field theory was born. Now, you are aware of other fields as well, which does not, which we are accustomed to thinking at the classical level, because you know that in order to describe electromagnetism, we write down Maxwell's equations. And when we talk in terms of Maxwell's equations, we don't really talk in terms of a quantum field. We talk in terms of what is called a classical field. So there is this field that you're very well aware of. You study in your undergraduate days. It's the electromagnetic field. And this was written down by Maxwell in 1864. And one of the predictions is that if you ignore source terms, then you can massage the equation to look like a wave equation. And it tells you that the wave is propagating at the speed of c, and c is what is the speed of light. And of course, such equations are compatible with Einstein's special relativity. You're also aware of the gravitational field. Again, this is something that we don't talk about in the quantum language. You don't say that this is a quantum field. We think in terms of equations, some gravitational field which gives us how, say, light bends around the sun, or how the Earth moves around the sun. So we talk in terms of Einstein's field equation. So this equation here is what is called Einstein's field equation. And of course, it has been very successful in describing a lot of phenomena. So this brings naturally the following puzzle. It's called the classicality puzzle. So here, I told you that here I talked in terms of a quantum field for the electron. Of course, we also know how to quantize the electromagnetic field. The quanta of the electromagnetic field is what is called the photon. The quanta of the gravitational field is what is called the graviton. But as undergraduates, you must be thinking then, why did we actually bother learning about the electromagnetic field as a classical field, the gravitational field as a classical field, but somehow we never thought about the electron as a classical field? How come we did not learn how to solve the classical field equations for electron? So how come we don't talk about the electron classically? Now, I wanted to discuss this a little bit because it's due to a beautiful argument due to Pauli and Peirce, and this is usually not covered in courses or textbooks. So I thought it would be fun to go through this argument so that at least you know what the reason is. So what does it mean when we say that we want to describe something classically? So you want to say that I have a field. Whenever you talk in terms of a field, you can do a mode expansion. It's like a Fourier series expansion. So let's talk in terms of a particular mode. So suppose you have a scalar field. You want to write it as some amplitude times some phase factor. So the way to think of the amplitude is that the absolute value of the mod square gives you the number of quanta n per mode. Now, you also know you can prove it, or you can think about it in Fourier space, that we must have some kind of an uncertainty relation of this kind, where the uncertainty in the number of particles in this specific mode times the uncertainty in the phase must obey some kind of a Heisenberg uncertainty relation of this kind. So to have classicality, we require that we have precise measurement for the phase. If the phase fluctuates too much, then of course we cannot say that it is classical. Maybe the fluctuations in the phase are quantum. So if something is classical, we require to know this phase precisely. So we can say that we require the uncertainty in the phase to be much, much smaller than 1. But this equation then would tell us that the uncertainty in the number of quanta will be very big, because otherwise you won't be able to satisfy this. But if the uncertainty in the quanta is also big, then you start worrying. Then in what sense is this classical? Because there's an uncertainty in the number of quanta, or number of particles in this mode. So for classicality, we must have the fractional uncertainty in the mode number to be small, which would mean that n itself should be much, much bigger than 1. And this immediately, you should recall Pauli's exclusion principle and say that for fermions, this is going to violate Pauli's exclusion principle, and that is why we do not have a classical description of the electron. But for bosons, we can be okay, and that is why we are allowed to think about the electromagnetic field and the gravitational field classical. So the quantum of each field corresponds to a particle. So you can sort of mentally visualize it as a field. Field means that it's a map from, so it's some kind of a function, and the input of this function are the space-time coordinates. So there is x, I, and t, and that outputs for u a complex number, And this field also, you can think of it as having fluctuations. And these fluctuations are, you can think of them as quanta. And these quanta of each field corresponds to particles. So that's what gives us photon, graviton, electron, Higgs boson, etc. Now, there's a technical bit. So in case there's an undergraduate who wants to learn about quantum field theory, the way to start would be to think about how you would classify particles. So you start by thinking about what is the space-time symmetry group, which is the Poincare symmetry. So this is the group of Lorentz transformations with a semi-direct product with the translations. And the particles are supposed to be the unitary irreducible representations of this Poincare group. And this is what is called Wigner's classification theorem. You don't have to worry about the technical details for this talk. You just remember that if I'm talking about one particle, then these states are labeled by the momenta of the particle and something that's you can think of as spin or the projection of the spin in some direction of the momenta. This is for massless particles, this is what is called a helicity. Or you can think of this as the J3 component of the angular momentum. And if you have two particle states, then they're basically tensor products of single particle states and so on. So in the standard model, we write a field for each fundamental particle that we know. And of course, you also know that when we talk about the standard model, we don't talk about gravitons, because that is something that we have not been able to do. We have not been able to incorporate the effects of gravity in the standard model. Although we know that there are situations where the effects of gravity must be very important. So this is roughly speaking where modern day, where we stand so far as modern day particle physics, modern day quantum field theory is concerned. So we know for a fact that certain particles are not fundamental and certain particles are fundamental in the following sense, that we say that the electron is fundamental because so far as we know, the electron does not have any substructure. The proton is not fundamental because we can do experiments, scattering experiment. We can send in high energy electrons and scatter off the proton. And we know that the proton is made of quarks and also gluons. So we know that proton has substructure. So these kind of experiments are what are called deep inelastic scattering. And this gives us the internal structure of the proton. And this, for example, happens, for instance, because these are charged particles, it could happen through an exchange of a photon. Now, this is not how the story evolved. So you would have thought that, okay, we now have a framework where we can do such calculations. We understand how these amplitudes are calculated. So definitely we must be on safe grounds. But you know, in physics, in theoretical physics, rarely does progress happen in a smooth, confusion-free manner. It is never the case. And it's fair to say that this is not how the story of quantum field theory evolved as well. So all was not well. People were very confused. And the reason for this confusion were infinities. So you may have heard that we sometimes describe quantum electrodynamics, the reason for which Feynman got the Nobel Prize, is one of the most accurate physical theories in existence. So the reason for this is that you can calculate what is called the anomalous magnetic moment of the electron, and you can calculate it in theory, and you get some answer and some numbers, and you can measure it in experiment. And as you can see, the agreement between theory and experiment is up to some humongous number of decimal places. So it's like 10 decimal places or beyond. In order to calculate the theoretical value, you require to evaluate what are called Feynman diagrams. And these Feynman diagrams sometimes have loops. So this is like a loop. That's what I was referring to. So there is some diagram and there is some loop here. So there is some loop which corresponds to an electron-positron pair going around. And the problem is that when you actually calculate these loops, each of these answers are infinite. People learned how to remove these infinities by a procedure called renormalization. And this is something that we really understand quite well now. And And you would say that, fine, I mean, we have a framework, although the answers are infinite, we have some procedure by which we can remove infinities and we can get these finite number. Clearly, the theoretical answer and the experimental answer agree very well, so things must be okay. Now, so what happened is, historically, quantum field theory began to be developed by shoving infinities under the carpet. And although this is sort of a derogatory way of saying it, it was done in a physical way. So it is not as if you were just taking the infinite part and then throwing it away. It is not like that, because if it was like that, your answers would be ambiguous. If you want to throw away infinity, you could do it as infinity minus infinity and plus constant, and that constant could be anything. So you might worry that your answers are regularization dependent, but that is not the way. It happens. It happens in a perfectly physical way, and you get a reasonable answer. And also, one of the successes of quantum field theory was that in the 1970s, we understood or began developing the theory of strong interaction, which is called quantum chromodynamics. And we also have discovered electroweak unification, had predictive power, it predicted the existence of new particles, and there was a lot of success. And it's perfectly accurate to say that the standard model has been tested a lot in the Large Hadron Collider and previous experiments. But it's also fair to say that perturbative QFT, where actually you pretend that there is a small expansion parameter, and you can talk in terms of Feynman diagrams at a particular order and next order and so on. That works for certain processes like QED, but it does not work well for low energy strong interaction. In the following sense, that if you ask anybody who is a practitioner in quantum field theory, how do you calculate the mass of a proton from first principles, they would actually struggle to give you a procedure without actually saying that you put it on a computer, use lattice quantum field theory, and then you do it numerically. Okay, and of course, another major thing is that this cannot be the final theory. The framework that we have described so far cannot be the final theory because we cannot include gravity. There are other technical reasons as well. In quantum chromodynamics, there are certain calculations which appear to be unnecessarily hard in the following sense, that there are certain calculations which involve scattering gluons. If you do pages and pages of calculations, and the final result literally fits in half a line. So obviously something is going wrong. If you require to work so hard to produce a half a line calculation, there must be a simpler way of doing that, doing the calculation. But another thing is that you appeal to authority, and Dirac, since it's fair to say that he is the reason why quantum field theory was born. What would Dirac say? Now, Dirac was a very unique man, and you would think that having a biography of a theoretical physicist apart from Einstein or Feynman probably is not a very interesting read, and you would be wrong. If you read Dirac's biography, which is titled The Strangest Man, it is a biography of Dirac by Graham Fermalo. It's a beautiful read because you get to know the inner working of Dirac's mind. Well, to an extent. I mean, it's difficult to actually describe the inner working of a mind like his. But let me read out a relevant portion. So in 1983, one of the original contributors to the development of superstring theory, Pierre Ramond, invited Dirac to give a talk. And at this point of time, although Dirac spent most of his life in Cambridge, after he retired, he moved to Florida. So Gainesville is a town in Florida. And Pierre Ramond was in Florida, so he wanted to ask Dirac to give a colloquium, and he was willing to drive him back and forth. And Dirac responded instantly, "No, I have nothing to talk about. My life has been a failure." This is the man who invented quantum field theory. He invented the Dirac equation. He's the reason why we understand electrons and positrons. And Fermalo says, Ramond would have been less stunned if Dirac had smashed him over the head with a baseball bat. Dirac explained himself without emotion. Quantum mechanics, once so promising to him, had ended up unable even to give a proper account of something as simple as an electron interacting with a photon. The calculations ended up with meaningless results full of infinity. And then he said, he goes on a tirade against this renormalization procedure that I told you. Dirac was a mathematician to the core, and he did not believe that the way that physicists were handling these infinities was mathematically sensible. And basically, towards the end of his life, he was a really unhappy man because he felt this was not the way that things should be done. Now, I should say that although Dirac had this viewpoint, he was probably being a bit unnecessarily negative. Because one thing is for sure, when Ken Wilson invented the renormalization group, his way of thinking about quantum field theory does give computational legitimacy to the way that we do quantum field theory. So the way that I have read this out is maybe thought of as unnecessarily negative. But nonetheless, you might wonder that there must be a more rigorous way, maybe a more rigorous framework, which is infinity free, which somehow enables us to do calculation. So why was it that Dirac was unhappy? So let me just spend 2 minutes explaining to you in technical detail. So what we do in quantum field theory is that we write down something called a Lagrangian. The Lagrangian has a kinetic term, there is a mass term, and there is also some interaction term, which tells you how the fields are interacting. Now, things would have been okay if you only encountered the first line. And then you said that this mass is literally something that I can measure. This coupling is also something that I can measure and be done with it. But unfortunately, this is not how we write down things in quantum field theory. We also write down the second line, which are called counter terms. So the role of the counter terms is to remove infinities. Now, if you are lucky, then the number of counter terms that you require to add are going to be finite. So schematically, what you will have in such a circumstance is that you do calculations, all your calculations will schematically look like infinity minus infinity, and you're left with some finite part. Dirac's mathematical side abhorred the way that this infinity minus infinity business, he did not accept it. And besides, what happens is that because you are removing infinity, you can also mentally think that, okay, I've got one kind of infinity, I'm removing it with another kind of infinity, but that could be ambiguous, so I could add some constant, so maybe the answer is ambiguous. But if the number of counter terms was finite, you could say that I'm going to make measurements, a finite number of measurements, and fix these ambiguities. And this works very nicely for QED and for quite a number of theories for the standard model, but this does not work for gravity. What happens in the case of gravity is that you don't require or don't have a finite number of counter terms, you require an infinite number of counter terms, which essentially means that to fix these ambiguities, you will require an infinite number of measurements, and so the theory does not have any predictive power. Okay, so to satisfy Dirac's mathematical rigor, we would need to invent a method that is manifestly finite with encountering no infinities. Is this possible? So before I go there, I think this is a good place to pause and ask if there are any questions.
Could you go back to the previous slide, please?
Yeah.
Yes, here where you are saying that you schematically do infinity minus infinity, it's not really like you're subtracting two different types of infinities. It is ultimately the same thing. There is a 1 by epsilon here and a 1 by epsilon there.
Yes. Yeah, I mean, it depends on which, how you're doing the calculations. If you're doing it in dimensional regularization, this is sort of right. Simplifying what I did, oversimplifying what I said, and it depends on your regularization method. Yeah, that is true.
True, but I mean, in terms of rigor, it's just my first point. You're not subtracting two different things. It's the same thing.
Yes. Yeah, what you're saying is right. So if you're doing it in this procedure called dimensional regularization, which itself could be thought of as a hocus pocus procedure, because you pretend that you're in 4 minus epsilon dimension, you do the calculations, and then you have a regulator in place, and then at the end of the calculations, after you have added the counter terms and you have removed the infinities, you throw the regulator away.
Right.
Yeah. Okay. Any other questions? Yeah.
Yeah.
Yeah, carry on. Yeah, please.
Yeah. Are these counter terms based on experimental methods, or like are they based on theoretical values of the first line you have written?
Yeah, this is a good question. So what happens is that the way that we think about it, it's quite different from the way that we are accustomed to thinking about in quantum mechanics. So in quantum mechanics, we have a Hamiltonian, and then all the parameters in the Hamiltonian are supposed to be physical parameters. When we think in terms of a quantum field theory, the way that we write it down, if you start off with something called the bare Lagrangian, then those parameters are not physical parameters. So whatever parameters are there in your Lagrangian are not physical parameters. Rather, you actually convert it into some amplitude or something that you can measure, and you express your answers in terms of those measurable quantities.
Okay, yeah. I think I got it. Yeah.
Yeah. Okay, so let me continue. So, is it possible to at least have some calculations where we can do something interesting, where the diagrammatic approach, Feynman diagrams, would require this procedure, but somehow this new framework, we can do calculations without encountering infinity. So this actually is not a new question. This has been thought about by a lot of people for a very long time. In particular, this was advocated by Werner Heisenberg, that we should only think in terms of things that we can observe. We should think in terms of, so say, from the perspective of scattering experiments, we should only talk in terms of S matrix elements. We should not talk in terms of fields and so on. This, what is called this S matrix, it basically takes you from something that you make at the initial time. It's some unitary operator that takes you from something that you make at initial time to something that you make at final time. And this was introduced in the physics literature by John Wheeler in 1937. And in the 1960s, a lot of people tried in working only with these observables, mainly by Jeffrey Chew, who was in Berkeley. And so sometimes you will hear the words, if you do some literature search about bootstrap, you'll hear the word Chew's bootstrap program. And the main goal of this endeavor was to do away with problems faced by perturbative quantum field theory and be in a framework which would describe strong interactions. That was the original goal. So a lot of people thought about that. So some of the names that a lot of people contributed initially: Landau, Chew, Mandelstam, Riemann, Martin. And then the philosophy behind this was that we think in terms of basic principles like Lorentz invariance, unitarity, and something called analyticity, which I'll try to explain if I get time. But you're thinking in terms of basic principles, and these principles are also include what is called crossing symmetry. So crossing symmetry I will describe in a bit. And the question is that, okay, so we don't talk in terms of a Lagrangian. So we don't talk in terms of a Hamiltonian to start with, or a Lagrangian to start with. We talk in terms of these S matrix elements. So we know what we are scattering, and those states are fixed by Lorentz invariance. Then we have unitarity, and then we have crossing symmetry. And are these constraining enough to give a theory uniquely or describe a theory uniquely? This is what is called the S matrix bootstrap. So let me tell you a little bit about crossing symmetry. So these four gentlemen are very famous, all of them. So let me give you just 15 seconds. So all of you can identify Einstein. Anybody wants to take a guess who this is?
Is that Tomonaga?
Tomonaga? I thought this was Yukawa. I think this is Yukawa. These two I know very well. So anybody wants to know who this is?
I think far right is Homihama.
Correct. Very good. And who is this? This is John Wheeler. So John Wheeler was Feynman's supervisor, PhD supervisor, and John Wheeler introduced the concept of the S matrix. He has made a lot of fundamental contributions to theoretical physics, including gravity. This is what his famous book, Meissner, Thorne, Wheeler. Okay, so this process, so why do I have this picture here? This process is the famous process called Bhabha scattering. So this is positron electron going to positron electron. And so this sort of sets up the skeleton of a scattering amplitude. So how do we go about describing a scattering amplitude? So it's an amplitude, so it'll be some function. So what will it be labeled by? So it's a relativistic theory. So the relativistic theory tells us that it must transform in a relativistic invariant manner. So what are the things that we specify? If you remember, I told you that Wigner's classification theorem told us that the external particles must be labeled by the momenta. So there's a momenta for this positron, there's a momenta for the electron, and then you can make invariants out of these momenta. There's a kind of invariance that you can make involve taking the sum of these two momenta and doing a Lorentz square of that. So that gives you what is called the S Mandelstam invariant. So this is called a Mandelstam invariant. It's basically the P1 plus P2 Lorentz square. Or you could also have a T Mandelstam invariant. So here there is another process which is basically the same process. So remember, time flows in this direction. So this is positron coming in, electron going out, exchanging a photon and then becoming a positron and electron. Or you could have exactly this same incoming and outgoing particles, except that it is happening in a slightly different way. The momenta that is getting exchanged is different. Here, the momenta that is getting exchanged is P1 plus P2. Here, the momenta that is getting exchanged is P1 minus P2. And it gives us Lorentz square, which is called T. So this amplitude is labeled by S and T. And it is also labeled by the spin of the external particles. So that's why this lambda 1, lambda 2, lambda 3, lambda 4 tells us what the spin component in the direction of the momenta is, the angular momentum component. So that is what it is. So crossing symmetry essentially tells us that I can take one of the particles on the left side of the process and another particle on the right side of the process and exchange them. So for example, for the positron electron going to positron electron, we can take the positrons and exchange them. And when we do the exchange, we also have to flip the sign of the charge. That's why when we do this flip, we get this process electron electron going to electron electron, which is another process which is called molar scattering. So this is molar here. So this seemingly different process of electron electron going to electron electron is actually related to the Bhabha scattering process. And so the original scattering amplitude, which is the function of ST with some helicities, is actually related to this the amplitude for this other process, which is a seemingly different process, via what is called crossing. So this is what is called crossing symmetry. And so it's basically the same function which gives you these same processes. Now I'm oversimplifying this a bit in the sense that when you actually look at the analytic properties of these functions, you might have to go through cuts. So when you go through cuts, you'll have to specify some rules, or if you're lucky enough, maybe you can analytically continue. There is some gap and you go through that gap. But that is not important. It's basically you have the same function which actually gives you the amplitude for different processes. So this would seem that, okay, fine, but what do we do with it? I mean, you have crossing symmetry, seems like a very complicated thing to involve. So imagine that you just equate these two. It's a function of two variables, S and T. It becomes a function of a different kind with the different arguments, but it is sort of the same function. And then how do we go about solving, for example, the expansion coefficients of these functions? So can this actually be solved? Even if we put an equal to sign here, can we actually solve that? So for conformal field theories, I will very, very briefly tell you what conformal field theories are. We have extra symmetries, and this gives rise to what is called the conformal bootstrap. And this was initiated in the 1970s, somewhat later than the S matrix bootstrap. But it is fair to say that except for d equal to 2, there was not much progress. Except that around 12 years back, these gentlemen, Ratazzi, Richkov, Tony, and Vicky, made a very non-trivial observation which gave us a numerical handle to solve these bootstrap constraints. So let me briefly tell you what bootstrapping CFDs are. So conformal field theories, you might have encountered. If somebody does conformal field theory amongst your friends, they will probably show you this plot. This is the phase diagram of water. And then they will tell you that, okay, we know about this triple point. All of you know about the triple point, but there's also this interesting point, which is called the critical point. And the critical point has extra symmetries called conformal symmetries. Now, I don't have time to explain how do we know that there are extra symmetries, but just take it from me that there are these extra symmetries. And so you can calculate what are called critical exponents. So, for example, how does the specific heat at this point behave? So things like that, physical questions you can ask at the critical point. And it turns out, quite remarkably, that many substances, different substances, actually have the same critical exponent. They might be different substances. So, for example, you could have carbon dioxide, and they will end up having the same critical exponent at the critical point. This phenomena is what is called universality, and that is one of the reasons why it is interesting. And you want to have a framework by which you can calculate these critical exponents. And a bit less surprisingly, the framework is again quantum field theory. This was taught to us by Ken Wilson. He got the Nobel Prize in 1982. And what he told us is that, look, through experimental measurements or whatever, you know that this critical point is in the universality class of what is called the three-dimensional Ising model. Now, the three-dimensional Ising model, for technical reasons, is hard to calculate. What you can do is pretend that you're slightly below 4 dimensions, so you're in 4 minus epsilon dimensions, and you can do perturbative calculations treating epsilon to be small. So this is called the epsilon expansion. After you're done with the calculations, at the end of the calculations, you set epsilon equal to 1, because you're doing calculations in 4 minus epsilon dimensions, you're setting epsilon equal to 1, so you're in 3 dimensions, and that will give you, or that is thought to give you, the critical exponents of the 3D Ising model. So the way that you do the calculations is to take your phi-4 theory and do a bunch of calculations, which involves calculating loops. And the state of the art for such a procedure is basically a 5-loop or 6-loop diagram. You have to calculate many diagrams. And imagine you are a poor graduate student and your supervisor told you to verify all these results. And you would really give an eternal scream. I like to call it the conformal scream. Because you would say that, look, there are extra symmetries and you're not using these extra symmetries. I told you that at the critical point, there are these extra symmetries. And yet you're giving me a framework where you have only used these symmetries. So this is a translation generator, this is a Lorentz generator. But what about these symmetries? So this is called the dilatation, this is called the special conformal transformation. So this is together, this forms a conformal group. You've not used these, you've just used these. So the bootstrap philosophy is that we are not going to talk about this Lagrangian. So here I had written down a Lagrangian, or maybe I'll show a Lagrangian somewhere, but then basically these diagrams come from a Lagrangian. The bootstrap philosophy is that we don't write down a Lagrangian, so we don't talk about a small parameter. We don't have to worry about the regularization or talk in terms of the renormalization group. Of course, there's a flip side. You are always at the fixed point because otherwise you cannot talk about conformal symmetry. And you're using basic things like conformal symmetry, crossing symmetry, and neutrality. Ultimately, rather than solving these Feynman diagrams and solving what I call the Kalan-Simonzik equations, you'll end up solving algebraic equations. And to cut a long story short, at the end of the day, what you get are algebraic equations, and you can manifestly demonstrate that these steps are all finite. So this is literally the kind of equations that you get. So you get some algebraic equations, coupled algebraic equations, and you calculate what are called critical exponents, which can be experimentally measured. These are the kind of equations that you get, which you can solve by hand or put on Mathematica or whatever is your favorite computer algebra software. And remarkably, at the end of the day, this agrees very well with Feynman diagram higher loop results. So up till 3 loops, the results agree. And these are manifestly finite. There is no infinity that I've thrown away. And this also gives new results for OPE coefficients. OPE are basically the interaction strengths between couplings. So you can have new kinds of operators that are getting exchanged. And the strength of the coupling there are what are called operator product expansion coefficients. And these things are difficult to calculate using the diagram. So, of course, I don't have time to technically tell you more about this procedure, but one of the things is that this appears to have something to do with what is called the ADS-CFT correspondence. So instead of the Feynman diagram expansion, we actually now have an expansion in what are called Wheaton diagrams. So Wheaton diagrams are basically scattering in anti-de Sitter space. And this forms for us a kinematical basis for expanding the correlators which have information about the critical exponent. So that's basically the take-home message, that there is something to do with the ADS-CFT correspondence which has never been completely fleshed out, but this is a procedure that works, which replaces Feynman diagram and gives us an algebraic way of calculating critical exponent. So you could have said that, okay, but this was for a very specific class of theories. This is for a very specific class of theories which have conformal symmetry. And you could sneer at me and say that, okay, this is an accident because of the fact that you had enhanced symmetry. Maybe you cannot do it for a general quantum field theory which does not have this enhanced symmetry. So can we bootstrap things which do not have this enhanced symmetry? So this is where I'm going to very briefly, in the last 3 or 4 minutes, I'm going to tell you about the work that was carried out with undergraduates and graduate student parties. The question is, suppose you're scattering mesons. So these mesons are very funny particles, because if you look at the masses of the mesons, if you open the particle data group handbook, it's a massive tome, it's like 1,000 pages or so, you will see that the masses are given in terms of a real part and an imaginary part. The imaginary part is because these particles have a finite lifetime, and that is why you have an imaginary part. But basically you have mesons of different spins, so these are spins of the mesons, and you can look at the real part of these mesons and identify that as the real part of the mass. And you have different kinds of mesons. There's some nomenclature. The thing in bracket tells you at what energy, what is the mass of the meson basically. So the sigma is supposed to be 500 MeV. This meson here is supposed to be 1270 MeV and so on. Now, remarkably, there's a very nice aside. If you plot the spin versus the mass, you get a straight line. This behavior is what is called the Regge behavior. And the explanation of this Regge behavior was a challenge in the 1960s, late 1960s, and is what gave rise to the birth of string theory. Now, to describe the scattering of pions, again, you go into some relativistic description. So you talk in terms of the Mandelstam invariants. So these are these Mandelstam invariants. So you have, you go into the center of mass frame, A and B are the incoming particles, and C and D are the outgoing particles, so they make an angle theta. This cosine of the angle is given in terms of these Mandelstam invariants in a certain way. You have this amplitude, and the amplitude you can do, like what you're familiar in quantum mechanics, you can do a partial wave expansion. The constraint of unitarity comes that these partial wave amplitudes here, these guys, are bounded. So again, you use basic things like unitarity and crossing symmetry. You use this constraint, which looks like a hideously nonlinear constraint because it's mod FL square. But very nicely, all these conditions can be recast into what is called a semi-definite programming problem. So maybe some of you have heard what a semi-definite optimization problem is, but basically it's an optimization problem. And for now, you require powerful computing clusters to be able to solve these problems, but hopefully that is going to change in the near future, where you can experiment on a laptop. And you can benchmark your theory space. There are some interesting results. So these crosses are things that you can calculate using a framework which is called chiral perturbation theory. There are some interesting models which are non-unitary string theory models which pass through the theory space. And when you use this unitarity constraint, you get an allowed theory space, which is much smaller. So this entire theory space is in this box. For reasons I don't have time to explain, the box is the range of the coordinates, x-axis and y-axis are bounded. It is from 0 to 4, and the y-axis coordinate is also from 0 to 4. But basically, there's a lot of white space, and the white space means that You cannot have a consistent theory living in this white space. There are some very interesting things like the standard model or the QCD value being very close to the edge of this allowed region. And one of the challenges currently is to explain why this is so. Or more specifically, you have some really wide space of allowed S matrices. So why should the QCD value be this point and not something else? So for example, why is QCD not there or there? Why is it this point? So what is the selection rule that you're going to apply to select out that particular theory? Why the standard model? Why the QCD value? And this does not have a complete answer as yet, and this requires creativity. So maybe some of you in the audience may have some creative ideas, creative input. So we looked at it using some quantum information theoretic ideas. So what we found is that we can calculate something called an entanglement power. So pions carry, like Lorentz spin, pions also carry something called isospin, and you can study entanglement in the isospin space. And you can ask how entangled are these particles or the pions, the incoming states or the outgoing states in the isospin space. So that gives you what is called an entanglement power. Quite remarkably, near this QCD value, so the way that you are supposed to read this diagram is that anywhere in the blue region or on the boundary, you've got an S matrix. So you can calculate the entanglement power for each of these S matrices, and you can get a continuum plot. This plot is like a continuum plot. It tells you that near this QCD value, there is a sharp drop in entanglement at low energy. So maybe something like this, you postulate that physical theories, because of low energy descriptions, should have as low entanglement as possible. Why that should be so is not very clear, but basically maybe you can think that nature is some kind of a quantum computer and it doesn't like doing hard calculations, and a drop in entanglement is going to make the calculations easier. That is why this drop in entanglement must happen. But basically something like that, some selection principle like that is what we're looking for. So I'm almost out of time. So in the last 1 minute, let me just point out that there's a beautiful story here which connects up the scattering amplitude ideas with 100-year-old mathematics. So depending on what your interest is, if you like pure maths, you'll find this interesting. Is basically the fact that I told you that this is the process that we are trying to describe, and maybe this virtual exchange is a very massive particle, and we don't really have enough energies to excite this virtual particle. So obviously not the entire amplitude is going to be important. Only a part of the amplitude will be important. So there will be some kind of a Taylor expansion of this amplitude, which picks out the low energy part. So this is what is called an effective field theory. An effective field theory tells you that for the low energy description, only certain terms in the Lagrangian are important, and it gives you a way to Taylor expand your Lagrangian, keeping in terms only keeping only those terms that are important at low energies. These Taylor expansion coefficients are what are called Wilson coefficients, and you could ask, okay, so C1 and C2 are the Wilson coefficients. So I have a theory space. So is my theory space like anything is allowed, where your observed phenomena are being described by some theory that is sitting in the center? Or is it like it's constrained and only a little bit is allowed, and your observation or observed theory space, observed thing that describes nature is sitting here? So this is what I would call constraining. This is what I would call not constraining. So these Wilson coefficients should be bounded for a theory space to be constraining. That is the message. If the Wilson coefficients were not bounded, you would say that everything is allowed. But if it is bounded, then you would say that not everything is allowed. And this connects up with what is called the Bieber-Back conjecture. So what happens is that in this huge continuum connection of S matrices that I showed you that are constrained by unitarity and crossing symmetry, you can construct these S matrices, which presumably describe some interesting physics. and you can calculate a combination of the Wilson coefficients. Remarkably, these combinations of Wilson coefficients satisfy what I call the Bieberbach-Rogozhinsky bounds. These apply for special kinds of complex functions, which are these are special kinds of complex functions which are called typically real. T subscript R stands for typically real inside the unit disk. Typically real essentially translates into a mathematical condition given here. The imaginary part of the function times the imaginary part of z is greater than 0. When that happens, Bieberbach in 1916 conjectured, and this was proven for typically real functions by Rogozhinsky here, that these Taylor expansion coefficients are two-sided bounded. So they are bounded on both sides. And that is the reason why the theory space actually takes on this form, not this form. Now, whenever you have bounds, as mathematicians, you ask, do we know of some function, or as physicists, we would ask, do we know of some theory that extremizes these bounds? So what kind of theories extremize these bounds? Here is the answer. So what happens is that if you impose that you have local description, local description essentially means that you don't have instantaneous transfer of information in some specific sense. What you find is that the extremal theory looks very simple. It is some combination of Mandelstam invariance raised to the quadratic power divided by some combination of the Mandelstam invariance. And this is nothing but the tree-level massless scalar scattering with a graviton exchange. So the extremal theory is as if it knows about gravity. So these mathematical considerations somehow reinvent gravity in a different language. So here is my punchline, and then you should ask me more questions. There are these new ideas which seemingly are esoteric because this is not something that you would learn in a standard textbook. I mean, we are just groping our way out there. We're trying to figure out what the correct rules are. Basically, we are saying that we want to go away from this Lagrangian description, this perturbative framework, and we want to think about quantum field theory in some new set of new language. So what we have done is we have found some interesting examples where finite methods exist. They give you results for things that you can experimentally measure. Of course, there is nothing to take away from Wilson's beautiful idea, because his ideas had physics justifications and they have proven to be enormously powerful. But at least for this example, where you have a manifestly finite way of doing calculation, if Dirac had been alive, hopefully he would have been happier with his own existence. But it is fair to say there's a lot left to do. This is a good time to actually get interested in the development of this redevelopment, I should say, or the reinvention of quantum field theory. One has to be creative, ask a doable and interesting question. These are not necessarily intersecting subsets. And the holy grail is, of course, to find the true theory of quantum gravity. I mean, I just said that in some limit, we know that there is going to be gravity from the description, but what actually is the true theory of quantum gravity? Is it string theory, or is it something else? Hopefully, these non-perturbative ways of thinking about things will give us the answer to that question. So I will stop there. Thank you for listening, and I think I am roughly speaking on time.
Hi, thanks for the wonderful talk. I have a couple of questions.
Yes.
Could you go to the river of S matrix? That's right.
Yes. There you go.
So it seems at point C there is another green line. So is that something special?
Oh, you notice that? That's extraordinary. In fact, the thing is that the chiral perturbation theory gives you this region here, but we actually found another interesting region which seems to have this Regge behavior. So these straight lines, which I showed you for the pions, they have, roughly speaking, the same kind of scattering lengths which are experimentally measurable. there's one particular thing called interacting range that people have not measured. But apart from that, this could also be a viable theory, So either this guy or this guy could be an equally viable candidate for the QCD theory. It is only that the chiral perturbation theory seems to prefer this, but I really don't have a way to rule out C. So it's quite incredible that you actually observed that.
So what you're saying is that there is some missing observable which could lead to this something near C being valid.
Yes, and if that holds, then that will be quite remarkable, because that would say that this chiral perturbation theory, at least the way that we have set it up, either is missing something, or maybe it does not capture the true QCD physics the way that pions work.
Okay, is this some low energy observable?
Yes, it's a low energy observable in the sense that you can actually measure what are called scattering lengths, but the subleading term in that is what is called interacting range. I think it, roughly speaking, translates into how far your massive particle force extends.
Right.
So that in principle can be extracted from scattering data, but these are hard measurements to do because pions are not stable particles. So you are not literally making external pions. You're basically inferring these results indirectly through some intermediate process where pions are being produced. So yeah, but hopefully one will have some way to measure these interacting ranges, and then one can actually say that whether this one or this one is ruled out. So you see, so I chose a particular value of the center of mass energy. It's a low energy value, and then for that I saw a sharp drop. So now this sharp drop definitely happens in the upper river. I did not have the plot for the lower river, but even for the lower river, you essentially have the same drop. So in fact, no, sorry, I actually do have the plot. This brown line is for the lower river. This red line is for the upper river. And as you can see, the upper river shows a sharp drop. Even the lower river, it has some interesting features. It sharply drops at that value. So there are two sharp drops in the lower river, unlike the upper river, which has only one sharp drop. But indeed, this portion, which you actually pointed out, this green portion, also has a sharp drop in entanglement. So there is something interesting going on there, which I don't really have anything definitive to say.
Right, so it's an open-ended question.
Yes. In fact, I would really encourage you that you think about some more creative way of probing S matrices. It's a very wide open territory, that you can come up with clever ideas of using some observable, maybe entanglement or something else. One just has to be creative enough to extract information from the S matrix.
Right. So my second question is, so the bootstrap formalism allows you to calculate Wilson coefficients or connect to Wilson coefficients, if I'm getting this right.
Yes.
So
you can, yeah.
So are measurements of Wilson coefficients a way to constrain the bootstrap formalism?
Yes, indeed, absolutely. So the bootstrap actually gives you a range of values for C1 and C2. So it does not give you a definitive value, because obviously you could say that, what are the things that you're supposed to input? You're supposed to input more physical information to get a definitive value. So there are two kinds of questions that you could ask. One is that how do I zoom into just this part? Can I have enough constraints, or can I give enough extra input from physics which will actually just zoom into the theory that is supposedly describing nature? So that's the question you could ask. The other question you could ask is that what is the largest theory space that is allowed by unitarity and crossing symmetry? So the answer that I'm giving you is, what is the largest theory space allowed by unitarity and crossing symmetry? So if you sort of roughly wrote down whatever terms are allowed in the Lagrangian by, say, symmetry, of course, you have to break this notion that, you're supposed to write down higher dimensional operators because you're in an effective theory. Then there is nothing that actually tells you that the coefficient in front of that extra operator, higher dimensional operator that you're adding, is constrained without appealing either to experiments or without actually just putting it in my hand. The question that we are asking is, does theory constrain these coefficients or not? And if so, by how much? So these are the kind of questions that one has been able to answer. We have not taken into account all the constraints that Bootstrap allows. So, for example, what we essentially did was take into account this part of the constraint. So it's just the absorptive part of the amplitude is less than 1 and is bigger than 0. We did not take into account the nonlinear constraint, which is this mod FL square is less than 1. So maybe if one did that in a clever manner, then this question could be, you could ask how constraining can the whole problem become?
Yes,
does that answer your question?
Yes.
Sir, I'm a first student and my entire understanding of quantum mechanics comes from books that explain it on layman terms and some of the reading that I've done. So so it might sound a little idiotic. So I was just wondering about that sharp drop in the kink you were telling. So I was just thinking that in Feynman's diagrams, Feynman explains the need for virtual particles using Heisenberg uncertainty principle by saying that there is essentially there is an uncertainty between the protons, and that's why that proton cloud is producing those particles. So I was just wondering if that kink in entanglement is being caused by this same uncertainty principle. That is this uncertainty because at that point, that becomes a measurement point or something, and we can further make it certain. And once we go further down the line, we are able to measure it. And once beyond that, again a point reaches where we can measure it. So quantizing uncertainty or something, because there exists. So I was thinking on that, where we want uncertainty and explain it.
Something like that is must be true. I mean, in the following sense that so you see there are two issues here. So one of them is that we are talking in terms of virtual exchanges. So virtual exchanges, this propagator here essentially looks like so. So this is 1 over k square, where k square is the momenta here, minus m square. So obviously this gets peaked when k square is approximately the mass of the virtual exchange. And so what you are saying is that if you're looking at tree level exchanges, then maybe the sharp drop is happening because there is an effective field theory description that we know nature must follow. And that is why the propagators look like that, and that is why there is a peak at k square equal to m square, which somehow is related to the sharp drop in the mean. That is a perfectly legitimate question to ask. And I can tell you that people have actually asked this question. So in fact, you just search for Seiler's beam, B-E-A-N-E. And in fact, in a paper that he wrote, I think in November or December, he actually had this conjecture that these drop in entanglement must happen because of particles going on shell. So,
I was saying, what if information is quantized? What if it's being conserved energy? What if quantum information is what nature is trying to conserve quantum information and not energy? Because if information is trying to be conserved, then that uncertainty principle should make sense.
Yeah, it's possible. So rather than saying that nature wants to conserve quantum information, you might want to say that nature wants to use as less resources as possible to do the calculation. I mean, if you pretend that nature is always doing quantum computation, so maybe that is the reason why you have this sharp drop. It is possible.
Sir, I have one more question.
Good ideas. I mean, these are definitely not uninteresting questions at all.
Sir, I have one more question. You had told about that earlier slide. In a slide, you had told about locality ruling out entangled conditions. Could you take that slide?
Sorry, which one now? Locality, this one.
Yeah, sir. You told negative powers are being ruled out by locality. So yes. I am just asking why should we rule out negative powers using locality? Because quantum entanglement in itself, breaks the laws of locality. Like
right. So
and especially
no, that's a good question.
Quantum entanglement breaks the rules of locality, and essentially, so for example, Dirac considered we were conveniently avoiding a negative square root of Dirac equation, and we came up with positron. When we considered it, we came up with positron. So aren't we like saying like negative by ignoring negative power?
Sorry, I was very quick in this slide. So this is a different notion of locality. So let me just explain this. So this notion of locality is basically the following: that when we actually write down the low energy effective action in terms of fields, we want to say that we are in the low energy effective action. We want to say that we are going to see gradients of the field or polynomials in that field. We are not going to see things like 1 over gradient acting on the field. So by ruling out negative powers of x, we are actually preventing that from happening. Okay. So in that, it is local in that sense. Why is that local in that sense? Is because if you look at the potential that local terms generate, they will, roughly speaking, be always of the Yukawa form. So the potential is going to be e to the power minus mr divided by r, which essentially means that because of this e to the power minus mr, the interaction strength is going to drop sharply. Okay. So it will be localized. So in that sense, it's local. Whereas if you had these other kinds of terms, it wouldn't look like e to the power minus mr divided by r. Rather, it will look like some positive power of r. If it is some positive power of r, the force becomes stronger as you go away. So the interacting force is not localized somewhere. It's actually spread over all the way to infinity. So that it is in that sense that it is local. So you want the interactions to be local. Does that answer your question?
Sir, the interactions no.
So interactions are never non-local. Yeah, because if the interactions were non-local, then you would be able to communicate at a speed faster than that of light. So in quantum mechanics, we do have non-locality, but it is a non-locality which is of a specific kind. You cannot communicate at a speed faster than that of light.
I was talking about the delayed choice experiments, which is hinting at a possibility. The delayed choice essentially something that is unexplained. So the delayed, I was just connecting that with this. So the delayed choice experiment, something similar happens, like something is happening there, and some kind of information either breaks the rules of locality or something like that. So I would your opinion.
Yeah, I mean, I think the notion of locality is a little different. So here, if you had these non-local terms, you would be able to communicate or send a signal faster than that of light. So that is why it would break causality, basically. So you would not have you would not have commutation between an operator that is within the light cone and another operator which is outside the light cone. So in that sense, it would be incompatible with causality. The way that we describe quantum mechanics, I mean, at least the relativistic way of describing quantum mechanics does not violate it. Okay, any other questions?
Hi, it was a very nice talk, and I have a couple of things I would like to get clarified. So the first thing is, initially you said that in the Bootstrap program there is no need for Lagrangian. Is that right?
Yes.
So then, do we still talk about coupling strengths and coupling constants in this context?
Excellent question. So in the you can. So the thing you might be worried about that, look, here we talked about an epsilon, and I said that there is no coupling constant. So where is that epsilon in these answers? Where did I get that from? So it turns out that the epsilon, which is related to the coupling constant in the Lagrangian description, is also related to 4 minus epsilon. So d equal to 4 minus epsilon, if we can set up the bootstrap problem in arbitrary dimensions, and we can set d equal to 4 minus epsilon at that level. And then, of course, you can expand in epsilon. So the coupling constants that we talk about are not physical. So these coupling constants are always translated into some measurable quantity. And then we express our answers in terms of that measurable quantity. So, so the answer that the bootstrap problem gives is always in terms of measurable things. We don't have to talk in terms of coupling constants in that sense.
All right. Okay. And one other question. So, in the towards the end, you had said that gravitational scattering naturally arises when we talk about the extremal bounds on this theory. So does this only happen at the extremal limit, or even for other cases, could that be a gravitational theory?
Yeah, that is also a very good question. You're asking that, so of course, true theory of nature should be gravity plus additional stuff. And so your question is that if I have gravity plus standard model plus something in some low energy expansion, then is it still an extremal theory, or is it somewhere going to be inside? So my understanding, yeah, that's your question, right? So that is mathematically what you're asking. So my understanding is that it is not going to be at the edge in this language. It is going to be it is going to be inside in the theory space. It won't be an extremal theory. But it's a very good question. I thought about it. I don't know the precise answer. So I just know that gravity is an extremal theory.
Okay. All right. Thank you so much.
Yeah, sure. Yeah.
Hello, sir. Thanks for the wonderful lecture. First of all, am I audible, sir?
Yeah.
So my question is that why we have different kinds of field for each particles? I mean, as a quantum field theory says that there exists a field for every particle, and the particle is itself a vibration in that field. So can't we say that there exists a universal field which is responsible for the existence of every particle?
Yes. Yeah. I mean, what you're describing is the philosophy behind string theory. So string theory exactly has that philosophy that we don't have to talk in terms of these multiple different kinds of fields. We just have a string, and the vibrational modes of the strings will correspond to different particles. So indeed, there is something like that, which people have been investigating over the last 50 years or so. So my take on that is that, you should think of this way of this bootstrap way of thinking to see if we can either reinvent string theory or invent the correct string theory, which is the correct description of nature. So if we reinvent string theory, then of course we are back to all the hard questions that string theorists have been facing for many, many years now. That how come we are not being able to describe or predict anything about nature. But hopefully we'll be cleverer this time, and then we are maybe with this endeavor in the next 10, 15, 20 years, hopefully within our lifetime, we are going to actually be clever enough to use these equations and identify what are the correct tools for describing something that involves a standard model as well as something that involves gravity, what that is going to be. Yeah.
Thanks.
Sir, I have final question. Sir, if you you had told that graviton exists, according to this theory, graviton should exist. So according to the standard model, every particle also has an antiparticle. So does this mean that anti-gravity is real? Won't that mean that anti-gravity is real if this is proved right?
No. So like the photon is its own antiparticle, the graviton will also be its own antiparticle. So you won't have anti-gravity because of the existence of the anti-graviton. So you won't have a repulsive force between two masses. It will always be attractive. And in fact, that's an excellent question. In fact, you can actually see this worked out. So you might ask that how do we know that whether a force is attractive or repulsive? And why should a spin 2 particle give rise to an attractive force? So this is actually discussed in Tony Z's book on quantum field theory in a nutshell. So I would very strongly encourage you to have a look at that calculation. It's a good question. What you've asked is a very sensible question, and but the answer is no. Yeah.
Thank you, sir.
Well, first of all, I would say that you develop a broad. I mean, it's impossible to become an expert in a particular area. As an undergraduate, you cannot hope to achieve that. But what you can hope to achieve is some kind of a broad brush overview for a lot of areas in physics, and not just theoretical physics. So one thing is that as physicists, you should also develop interest in experimental results, because physics ultimately is guided by experiments. And you should not be of that attitude that, okay, this is experiments, I don't care about it. I'm just going to focus on the mathematical side. Because there are pitfalls in that way of doing things, which you are aware of. That if you're not aware of what nature is telling you, then probably you are in the wrong direction. I mean, whatever you do might be might be in the wrong direction. So you should have this. I'm not saying that you have to do experiments. I'm saying that you have to be interested in experimental results. The second thing is, for sure, there are certain tools in theoretical physics which are very handy. So one of them is, look, you cannot be an expert. Don't expect that you're going to be an expert in doing integrals by hand or anything like that. So learn a computer package, maybe Mathematica. Learn how to use Mathematica as well as possible. So learn the concepts of mathematics, but learn how to use a computer package to play around with. So a theoretical physicist's playground is basically these kind of numerical experiment, or the experiments that we do on Mathematica, because that is where we are playing around. And in present day, you can't expect that you are going to be like Einstein and do calculations by hand. There are several calculations even in this kind of program which cannot possibly be done by hand. You have to use a computer algebra package. So if you don't know Mathematica, then you should try and figure out how to learn Mathematica and basically get into the habit of playing around with it. So that's probably the second piece of advice that I can give you. And the third piece of advice that I can give you is that be passionate about the history of physics. So this is something that Weinberg says in his books as well as in his interviews, and there is a reason for it. The reason is that, people have, theoretical physicists have a very small footprint on this world. First of all, I mean, you're not doing something so exciting that you are going to necessarily become world famous. But at the same time, you have a duty in actually contributing, so that as a worst case scenario, at least your contribution is recognized in some textbook. Now, if you don't appreciate the kind of hard work that goes into making discoveries, and the kind of enormous mental energy that goes into making that discovery, then actually you will miss out on one key aspect of doing theoretical physics. You should know as to how, say, Priestley discovered the gases, the constituents of the atmosphere. You should know why that was important. At the same time, you should actually know, why Raychaudhuri is famous in the Indian context. At least know what is the importance of the Raychaudhuri equation. So then you'll have some role model to go by. So whoever that is, it does not have to be somebody immediately eminent. So I would say that you just first of all, don't ignore experimental results. Experiments are very important. First. Second, get into the habit of playing around with a computer algebra package, because don't expect that you're going to just open a handbook of integrals and be able to do calculations in your head. That rarely happens. We do a lot of experiments using computer algebra packages. And the third is be passionate about the history of physics, because that will give you some motivation. You will see that what kind of pains go into producing a result which can be called a theorem, or which can have a name, which might be named after you, so to speak. And it's good to be aware of the historical development of a particular field, because it will tell you that if you're confused, you have every right to be confused, because theoretical physicists are most of the time confused, and you should not be frustrated at these confusions, because people have gone through these kind of frustrations over several years. So, and if you appreciate that, then you will find that you'll be more at peace with yourself. I think those are the things that come on top from top of my head. These are the kind of things that I usually tell my graduate students as well, because sometimes they get stuck with calculations, and I say it doesn't matter. I mean, you're expected to be stuck, so you have to go dig deep and figure out why you're stuck. Yeah. Thank you very much. Thank you for the wonderful questions. All the best. Bye bye. Stay safe.